first time. All right, anyway, we are doing the recap so far. Okay, let me take a look at it. It says create output stream. Okay, skip cleanup this. It is saying it is trying to store the file at the right location. Go up, please. Go up. I see. Okay. Go further up. Okay, go up. All right. Now slowly go down. Let me take a look. The input is correct. So it's able to read the input. And okay, okay. Create block output stream. Connection is refused. Go down. Go down. There are 5 data nodes running and 6 are excluded in this operation. Okay, so most likely one of the data node has gone down and probably you are on it. But it must have saved the results. Did it save the results and in the end, even after giving the error? Looks like it did something. Go down. Yeah, each of the stays is getting converted into. I see, I see. Let me take a look at it maybe after the session. There's something strange. All right. Let me take a look at it after the session. Probably something is wrong there. Okay. Don't worry, Ajiankun. I think after the session, I'll take a look at it. Okay. I'll try to do the same thing from your login ID. That should be better idea. Okay. Okay. Maybe is it your quota is full or something like that, because around you get 4 GB of quota, including all the data, including replication. So if that gets full, then you are not allowed to create folder or files. That could be one of the reasons. Just try creating or copying a small file or folder to HDFS, then you will know. Okay, now coming back to questions from Sunny. Okay, first is when scoop command is run, by default, it takes 4 mappers unless specified by us to read the data in parallel. Okay. By default, it takes 4 mappers. No, I don't think so. By default, it takes only 1 mapper. Okay. So when you run scoop command, it basically uses a single mapper, or Number of mappers are a function of the data being copied, but since here it cannot predict the data that's being copied, okay, because the data is elsewhere, not on HDFS. Therefore, the number of mappers is a function of what you provide. So by default, I think it is one mapper. Now, question is, even if there are four mappers, if we explicitly specify that we have four mappers, what happens when the mappers break during reading of data? These mappers are run elsewhere, and there's a fault tolerant associated with mappers. Okay, it runs on any other machine. Now, second question is, very good question, Sunny. Second question is, what is the main difference between generalized connectors and specialized connectors in Scoop? Specialized connectors can work with almost all of the database servers. Then why do you generalize connectors? Okay, very good question. So question is, there are many kind of connectors. Okay, connectors, there are many connectors which are provided by default, and some you can create by yourself. So honestly, you would hardly ever need to create any connector because of many reasons. One, by default, almost every database supports JDBC, Java Database Connectivity, same package, and Scoop supports that. Therefore, 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 specialized connectors are not really required. All right, so that's the difference. So specialized connectors are only required in certain circumstances. Okay, so I think the generalized connectors are good enough for connecting, but the general thumb rule is, in case of connectors, that whatever gets the work done faster, we pick up that particular connector. Okay, even when you're trying to connect to a database from Java, there would be multiple drivers and multiple connectors in a normal Java code, and or normal C# code, or normal uh, say PHP code. There'll be multiple drivers available from multiple parties. So whatever gets the work done in the most efficient manner is the one we use. Third question is how to deal with complex where clause in scoop command. Okay, okay, good question, Sunny. So, so what do we mean by that? The question is, the complex query could be after joining, right? After joining something, a result is being returned, correct? So the better way of handling is that you use that complex query on the database side. Okay, let that complex query be executed by database, because database can generate a table, and that table can be saved, and we can read data from that table from Scoop, so that Scoop can take advantages of various properties of that table. All right, such as if you have a table having an ID or primary key, Scoop by default considers that column as the reasoning behind uh, say updating data. So I'll explain to you. So in many cases, you might have to have incremental updates. Incremental updates are that on the left hand side you have data that is being table that's being appended to very frequently, and on the right hand side you have, say, HDFS file or a database table in Hive. Now, from time to time, you want to import data from this ever increasing table from database to our Hive. Okay, so in these cases, Scoop need to keep track of what all record have been copied. So if your table is having an ID, you can tell Scoop command to use that ID as the way to decide whether the record has been copied or not. Or you could define a timestamp table, and based on the timestamp table, Hive will do the work. Okay, all right. Now, question from Sunny is, while reading data from database, if the number of record changes, say 3 records got deleted, so will Scoop fetch all the deleted record also? No, it would not. If the transaction finished before Scoop talking to the database, okay, whenever we are doing something in case of database, the it is done inside a transaction. And this transaction could run across multiple queries, or it could run uh, only across just one query. So this transaction, in case it finished before Scoop started talking to the database, then Scoop will get a fresh, Scoop will get the updated data set, which means these records will not be available. If transaction got executed in parallel to Scoop, so Scoop is reading and transaction is writing, unless, so in these cases, Scoop will get the data before the transaction, before the deletion of those records. So Scoop will get those 3 records as well. Okay, but generally when generally we have something called a locking mechanism. So the moment a transaction start modifying a record, others are not allowed to read it. Others generally wait to read the records. Okay, so that's the way it is. Yes, George, Scoop does partially handle structured data. It basically imports structured data. Okay, did I make sense to you, Sunny? All right. Next question was how to deal with certain values like null, which we do not want while importing. So those things you can put in the filter query or where clause. Okay, that's where the where clause comes into play. We could say where this particular column is not null. And next question is how to deal with tables not having primary keys. So if you do not have primary keys, you can make some other criteria. So there is no issue as such. I'll be very, very honest with you. So for Scoop, it does not matter whether table is um, having primary key or not. It doesn't matter. Okay, the only cases where it matters is one, you are doing incremental import. Okay, you're doing incremental import, or you are doing update. There is a mechanism by which you can say that Scoop can update the record, which means it can delete the new records and create the new records or update the existing record. That is also possible, but for that you would need a criteria for ID. And the third case is, while you might need a primary key, is in the cases where you are importing data to HBase. Okay. So I think, as per my understanding, if you try to import into HBase, then it would say that it would by default try to use a column name ID as the ID, as the row key. Okay. If it doesn't find a primary key, it would basically prompt you to say to specify the ID column. Okay. So Sunny says that I tried importing all the tables and it failed. Let me take a look at. So you just send me your screenshot. I'll take a look at it. It should not generally fail. It should generally fail when you are trying to do incremental or update imports. Okay. I see. I see. Scoop import all tables, connect to JDBC this, username this, and -p. All right. Okay, doesn't look like a problem, but I would love to see it, how it goes. Okay, I like to try it out. All right, let me make a note of it. All right. Yes, go ahead, Sunny. A question from Sunny. What about native drivers? Will Scoop pick native drivers over JDBC driver where translation won't be there? Okay, good question. So generally, we specify the driver that we are going to use. It would not really switch the drivers by itself. It'll basically wait for what you have tried to configure, or it will let JDBC choose how to connect to a database. All right, but I would love to take a look at what does it mean by how does it behave in case of native or JDBC drivers. All right. Generally, what happens is for each database, there are multiple vendors who provide the database driver. Okay, and I remember when let's say I was trying to interact with Sybase. Sybase is one of the databases earlier that Microsoft had purchased, and Microsoft has now renamed it to Microsoft SQL. So that database called Sybase was having three different drivers. One from some open source world with, of Java, and then second one was from Microsoft themselves, and there was a third one. So they all had different qualities. So in these cases, what we do is we basically create our dummy connector, which internally uses JDBC driver, and we specify that this is our class name, and whatever is required, whatever jar files are required to execute this, we put in the lib folder and try to execute scoop with the modified connector. Okay, so we just create a wrapper and start using that. All right, and then see whichever works. All right. I'll take a look at it more closely. How does the behavior of native driver looks like in case of scoop? All right. Any other question at this point? All right. Great. Yes. Good. So let's move on. So till last Sunday, we talked about transformations. right? And then we were about to start the discussion on actions. Okay, it, so is there a question related to transformations? Please feel free to ask, because that's the only way to clear the doubts. It takes some time of trying out these RDD operations to make a very clear distinction between transformation and action. And honestly speaking, even though Spark guys say that there are something called transformation and action, most of the functions are a combination of both. Okay, I'll show you and you will realize that part. So in our word count kind of cases, what we did was we loaded the data, did some transformation, made some modifications to the things, and then we said take, or we said save as HDFS. Now, when we said take or save as HDFS, only then the actual computation started. Till then, it was just waiting for our orders. It was just building up the RDD. It was just building up the list of things to do. Okay? So unless we execute an action, Spark just keeps on making notes of things to do, and that's the way it works. That is the way it works. So it keeps on making notes of the entire way of transforming the data, and then once it has built the list and it is done with building the list, then it moves to it, and we execute the action. Then it executes the entire okay, it executes the entire RDD graph. Okay, so here, going back, so the first few lines up to the take are basically transformations. Up to these lines, first one loaded the line, second one converted lines into words, converted third one converted the each word into a tuple of word comma one. Fourth one said reduce by key, meaning group the data by the key and then sum it up. And then these two lines are important. This one is an action that just executes the entire flow and gives you first 10 records. And this one you see here, this one basically executes the entire flow till this point, and then uh, saves the result in the disk. Yes, it is same as pick. Thank you, Sudhakar. Execution starts with dump or save. It's just that Spark has further generalized the concept. Okay, both of these are based on a particular component and the paper that was again published by Google called Sogel. There was a component called Sogel. I think it was Sogel, Sawzeel or Jell. It's the same way. And this is called lazy evaluation. So Spark driver kept on waiting for you, okay? And it kept on making notes. It kept on making notes here. And the moment you said take, only then this got executed. Okay, a question to all of you: does save as text file execute take as well? Quickly, when we say this, will it do this also? Okay, let me ask you again. Okay, let's say your code looks like this. Let's say your code looks like this. There's no or. There's no or. Your code is like this. First you said take, the entire flow got executed, and then you said this. When you say save a text file, which of these statement it won't execute? Will it execute? It should. Would it execute line number 23 when we execute line number 24? Okay. Yes or no? When we execute line number 24, does it execute line number 23 as well? No, it does not. Because this does not depend on this. This depends on words KB. Words KB depends on words RDD. Words RDD depends on lines RDD. And lines RDD depends on this data. Right? And therefore, this statement, and this statement don't depend on each other. Okay? Now, another question, let's say what we do is something, again, something like this. Okay? What we do is we basically say this. Now, when we execute this, let's say this is the code that looks like what we have. Okay? This is the code that that's what we have. And or let me say just for the heck of it, I'm trying to do something really strange. And all right, now this is our code. Do you see the code? What would it do? We loaded the data, we defined words RDD, we defined words KB, then we defined the output. And this one, let's, okay. So when we execute this one, what will it do? Okay. Yeah. So what will be the output here at this point? What will it save in the file? This is the code. So the last line, 25th line, at this point, what will it do? Yes, it will save the result of lines.rdd.map, lines.rdd.map, correct? It won't save the word count. It would not save the word count. No, it would just save the same lines RDD, comma 1. Okay, this is what this. So the result would be this comma 1, this comma 1, and this comma 1. This will be the result in the file. Not clear? Okay. It's very important because these are the these are building blocks. So that's why I'm a little more focusing on what it means by. So you can always think of each RDD like a view on a table. Okay, here we have lines RDD. So there is a file big.txt in HDFS, correct? And then we have lines RDD. Okay, after reading this, after loading this file, it will create lines RDD. So this is a dependency graph. Who depends on who? Okay, that's what it is. Okay, so we have this, and then we have, okay, and we have output. Good. So far good. Yes. Yes. Good. So somebody has asked me earlier, what happens if we reassign the value? Now we are saying in the next statement, first we said take. The moment we said take, it'll basically execute all of this. Okay. When we say take, this entire thing gets executed. Okay. When we say output dot take 10. So this entire flow, loading of this data into lines and converting into words, and then converting each word into key value, and then displaying the result. This entire flow will get executed. But what we did was at later point of time, we defined a new variable called output. This is basically defining a new variable called output, which means this variable gets overwritten. And instead of depending on words kb, now in the second time, it basically depends on big.txt. Sorry, line.txt, line RDD. Okay. So when we call this, it's going to only execute these two parts. Yes. Vikas, I will answer your question. It's a very good question. It won't split into words. Why? Because of this. Because this output variable got overwritten because of this statement. Okay, here we are saying output is equals to linesrdd.map. Okay, we are saying linesrdd.map. We are going to operate on it. Okay, or you can think of this as a separate variable. Think of this as a separate variable, and this is getting deleted. Make sense to you? Very good question, RS. All right, I'll answer. These are very good questions asked. I would love to answer those questions. Okay, so this is a very important thing. What we did is to take this example because we have been very used to our traditional programming language where when we say print, it prints. When we say x equals to y plus 1, the value of x gets updated immediately, right? It doesn't wait for some action to happen. So it's kind of lazy. It's kind of, it waits for action to occur so that transformations can occur. Okay, till that point, till the action has occurred, transformations are nothing but statements. It just keep making the notes. You remember the waiter in a restaurant, right? Imagine that you went to a restaurant and you called the waiter that give me, okay, you called the waiter and you said that give me give me one juice, give me, and you were about to order second thing like sandwich, but the waiter went to the kitchen and to get the juice. Okay, even before you could place your second order, right? You could say that I needed a sandwich, but the waiter has gone to the kitchen to get you the juice, right? That's non-lazy way of executing. It executes then and there. Okay, but the nice waiter waits till you have finished your order and he confirms and then goes to the kitchen, places the order, and also optimizes the things. For example, you and your friend, both of you went to the went to the restaurant and both of you have placed an order for an omelette. So instead of cook preparing omelette at two different times, the cook will find it easier to prepare both the omelets at the same time, right? The whole process becomes more optimum. Similarly, if me and you, we both went to the restaurant and we both ordered, say, salad, same salad, so it becomes very easy for the cook to prepare uh, two salads in a single shot. Okay, so this is the optimization. This is the optimization. In the same way, if let's say we order a similar thing here, we are saying flat map twice, or we are saying these two transformations. We are placing one order. We are saying uh, first get me this file. Then once you get this file, apply flat map on this, and we're basically placing order and it's making a note of it. The driver is our waiter. It's making the note of it, and the kitchen is on each node managers where the things are getting executed. Okay, so we're placing the order that can you give the flat map, then the map, and please notice that if let's say we have some more maps here, for example, convert like we are executing something like clean the records, okay, like can remove the special characters or convert to uppercase. Okay, convert to uppercase, and here of course we'll not be keeping it like this. We will could be chaining it. This one will look better. So like load here, and before doing the flat map, before breaking it into words, we could do map and say to upper, convert it into to upper, then again another map and say uh, say um, say remove non alphanumeric. Okay, these are the two functions that you have written, which basically removes the special characters from the each line. Okay, and then you split. Okay, so what you see here is an interesting exercise whereby we're cleaning the data before cleaning the lines of string before we convert it into words. Okay, so we have multiple. We ordered first to upper, then we ordered second thing called execute this particular thing called remove non-alphanumeric, then break it down into this. So instead of this waiter called spark driver running away to the kitchen on every time we are ordering something, it's basically waiting for us to finish the work and then optimize it. And how would it optimize? It'll combine these all steps into single, right? Because we also could have combined it into a single function and then hand it over to Spark. Did I make sense? So, so the waiter analogy is something you have to keep in mind, that there's a waiter who is a little lazy unless you say to the waiter that now you go to the kitchen, please place my order. Okay. A question from Vikas. At what my point of time lines RDD and words RDD we'll lose the data mapping. So these are just two variables like object. They are very thin object. They don't have any data. They just have this mapping, as you say, and they will expire as they go out of scope. Just like in a Java class, when a variable is out of scope and is no longer in use, Java will do the garbage collection. So it is not up to the Spark to, to expire these variables. It is up to the Scala, which means the Java compiler, and hence it will follow the same rules as Java objects do. Okay, did I make sense to you? And RS, was I able to explain what's the advantage of deferring the execution? Okay. Question from RS. In this example, each statement is a different activity. Being lazy, are we not loading the complexity of last statement output and unnecessarily wasting the CPU time during the lazy time? So this lazy time is what time? Can you help me understand? This lazy time is the time when we are writing the code. Okay, when we are writing the code. Okay, and this time, if we are actually handing over our code to Spark, this waiting time between this line and this line is almost 0 milliseconds. Why? Because it'll get submitted. The interpreter will start reading from line by line and start processing it. And as soon as it reaches an action, it would be executed immediately. Okay, did it make sense to you? These are very good questions. And yes, keep these kind of questions coming, because answering to these questions and understanding the basics is more important than mugging up all kinds of transformations and actions that are there. Okay? Understanding the behavior of Spark is more important. Okay? And practicing, and to understand, you might have to try out these things, try out this kind of model, this kind of execution, and notice what goes on there. Okay, all right, great set of questions. Wonderful. All right, so yes, what happened to this guy? Okay, wonderful set of questions. Moving on. All right. So action causes the full execution of transformations that have led to the all the chain of transformations actually. Okay. So an action involves both Spark driver as well as nodes. So for example, count. What does count do? When you say rdd.count, it will first count on all the nodes and then bring that count to the driver, and driver will sum it up and give you the results. Okay. So as simple thing as count is also, it also is distributed. All right. So an action looks like this. Something happens here, something happens here, something happens here, and something happens here. And all of this result is gathered at the driver level. Okay. So you can see, is this example clear? Here, first we are taking a huge number of records. Then we are converting that into an RDD by saying sc.parallelize, and then we are defining a function called multiply by 2. Afterwards, we're defining a function called multiply by 2, and then we are saying map. We are saying nums dot map, and we are passing the function. And this way, this function is going to be called here, 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 and of course, it'll be called at the later point of time when somebody calls an action. So when somebody calls dbls.take, it'll first figure out who is dbls. Okay, dbls is nums.map, fine. Then who is nums? Nums is sc.parallelize arr. This gets executed immediately, and then rest of the things get executed. Okay. Now, there are some more very important transformations we would like to cover. Okay, very good question, Mohit. How is the coordination between nodes done? What goes in background in merging the output? Okay, you will see this as we go ahead. Okay, the coordination, basically this driver continuously talks to all the nodes. Driver knows that these are the nodes doing the execution. Okay, driver knows that part. So driver could always talk to a particular node and say that, can you give me first 10 records? All right. All right. As you go forward, as we move, it's a very deep question, and you will understand this as we move forward. All right. Now, moving ahead. So next is a very interesting transformation called filter. Let us say you would like to remove certain words, some stop words, some, let's say you want to remove all the prepositions or the and all the articles. You would like to remove the prepositions, articles, all the punctuation marks from our big.txt, from our data before we process. So in those cases, you could use things like filter. Or filter means there is an RDD, you want to remove certain records from it. You don't like certain records. So you will write a function which will be like a filter, and you hand over this filter to, you'll hand over this function that basically is the sieve. Who understands what's a sieve? So sieve is something that does not let something pass through, right? So we hand over this sieve to Spark and say that, can you please use this criteria or the sieve to filter the data? So that function here, we have defined a function called isEven, which basically divides the value by 2, and if the remainder this percentage sign means remainder, and then equals 0, right? So here the remainder, if remainder is 0, it returns true, which means in case of even numbers, this function is going to return true. So all the even numbers will be retained and all the odd numbers will be dropped. For example, in this case, we have these records. Each record is a number here. Okay, each record is a number. Why? Because when we parallelize an array, so whatever is the individual value of an array, that becomes the record of an RDD. Okay, and then when we say nums.filter, and on execution in when execution happens, this isEven will be first tried on 1, 2, 3, 4, 5, 6, and 7. If isEven returns true, isEven function, this had returned true, it could have been, its output could have been in another RDD called evens. But since it returned false, Since it returned false, its output was not kept. This returned true, therefore output was kept. This returned false, so it got discarded. It returned true, so it was kept, and so on. So while creating a filter, all you have to return is true or false. The Boolean value signifying whether to keep it or drop it. Okay. A question from Tamika. Filters on this array. Yes, that's right. From Rahela, can we use Sunny's question of removing none value, if any? Yes, you can do that. Okay, you can do that. A question from Ravi. What is the degree of parallelism when sc.parallelize is called? Wonderful question, Ravi. Yes, wonderful question. Yes. So, okay, it's a good question. Let me try to answer this. What is the degree of parallelism? Degree of parallelism is a function of number of partitions that it creates. These are records, but they could be in the partitions. We have not demonstrated that part because generally in the big data computation, the partitions, our code should be such that it should not depend on partitions. So these 4 records could be in one partition and these 3 could be in another, and so on. So partition is just bunch of groups similar to input is split. So, but bunch of records similar to input is split. So here, what we have is the general algorithm in the case of Spark is that if you say sc.parallelize and if your data is small enough to be able to fit on one of the nodes, then it would not put it on multiple machines. And on each machines, based on number of CPU cores, it creates those many number of partitions. And in this case, it is most likely going to create 2 partitions because it's going to be on a single machine and that single machine contains 2 cores. Therefore, it's going to create 2 partitions. Did I answer your question, Ravi? Okay. A question from Ravi is filter a library method? Filter is a method provided by RDD. Nums is an RDD, right? Nums is an object of um, parent class called RDD. This nums provide a function called filter. Good question, Nitesh. So a partition is a function of both node and CPU. If your data is located on multiple nodes, then let's say your data is located on 3 nodes. So and all these 3 nodes each have dual cores. So 3 into 2 other processors. So there'll be total 6 partitions. Okay. So question from Ravi. So when those partitions are made, the input data is split into 2 partitions randomly, not randomly, it's sequential. So when we load it big.txt, line 1 will be here, line 2 will be here, line 3 will be here, and line 4 will be here. Okay. And so on. It's a very important question. So data is generally in the same sequence as the input data. These are very important questions. Okay. All right. All right. Did I miss anybody's question? In case of bulk data, how the data processing will be handled in memory? Quick answer is it is not. Okay. In case of bulk data, this data, like for example, big.txt, it was not really loaded into the memory at any point of time. Only parts of it were loaded into the memory when the action was being executed. Okay. And sometimes if we really want to make our operations faster, what we could do is we could say On every RDD, we could say cache, and that would load that data into the memory. Okay, into the memory, and that will remain only during the execution of an action. Afterwards, that cache might disappear. Good. All right. Now, there's something new here called flat map. So flat map is something that converts a single record, like lines RDD has two, this line and this line, and two words returned an array by splitting the line, right? Therefore, two words would give us this array, and two words will give us this array from this. And then this flat map basically joins that into an RDD where each record is the values returned by by a flat map method. Okay, do I make sense? So what is it that we are trying to do? We loaded this data, okay, whereby we have got two records. Then we executed this one, which converted the records into words, the lines into words, and then so flat map converts one record into many records. Okay. Okay. So number of output records in case of flat map could be more than input records. Is that true? All right, let me try to talk about in this context. I'm making it again back to what I was talking about. So when we say count basically returns number of records. So is this true? Is this true? Right. This is not true. Okay. This is not true. Yes, other way is possible. That too is possible unless there could be a scenario where both are equal, where every flat map returned one record. That could be a possibility, right? Good, good. So is everybody clear about flat map? Map we have already talked about. Question from Mohsin, is Spark using HDFS node for program execution, creating RDD, and then giving results back to the driver? Is basically using Yarn node manager, okay, and resource manager. And while reading the data, Yarn will talk to HDFS, and accordingly, the places where this logic is going to get executed would be nearer to the data on the node manager. Okay? Remember our discussion from the architecture time? All right. So if we say this kind of thing, okay? If we say this kind of thing, so instead of a common question is that we have written this two words function It returns an array given an input value. What would happen instead of flat map? We used map. What would happen in that case? Can anybody guess? What will be the number of records in output? In this case, where we have two records in input, we created lines.rdd, and then on lines.rdd, we say map instead of flat map. What will be the counts of word.rdd? Yes, it'll be only two. It'll be something like there'll be two records. Each record is an array. Okay, each record would be an object which is an array, as opposed to this. Good. All right. So this is what would happen in case we used map instead of flat map. So we cannot do word count on this because there's an array, and therefore we can, when we say reduce by key, it's going to group by the whole array, which is not really right. Okay. Now there are very nice functions provided by Spark, such as union, in which you can concatenate two two RDDs into one. Okay. Why would you like to union, for example? Let's say that there is some data, there are some records from production. Okay, there are some records from production that you would like to clean up. Okay, that you would like to clean up. Okay, actually, all right, all right. So I hope you will be able to hear me now. Yes. Actually, while testing, I muted it, and then I was wondering. Okay. Okay. Sorry, extremely sorry for this. Yeah. Okay. All right. So I was talking about this. So you can union the results of these two filter and then get it. So you can create as many of such permutations as required to achieve your output. Okay. So we learned about map. We learned about We learned about flat map. We also learned about union. And of course, take and save as text file. Okay, these are the functions provided by the library called RDD. Yes, okay. Sometimes you want to bring entire data to the driver. Although it is, a crazy thing to do, be aware of this. It basically is opposite of parallelize. Parallelize distributed the in-memory array into RDD. Okay, in-memory array. I'm going back to here. I think we missed here. Let's say input RDD is the data loaded from the logs. Each line, each record is the line from the logs of your web server. So you did filter. You said remove the lines which are not an error, okay, by applying filter, or keep the lines which are only the errors, right? Similarly, warnings, you only kept warnings. And then when you union them, it's basically concatenating. There is no sorting happening, no grouping happening. So there is no point of any key. It's equal to cat this with this. Concatenate these two. All right. And generate a new RDD. Make sense, Sudhakar? Yes. It's like appending data. So this is also called RDD lineage graph. Okay. It's a directed acyclic graph, meaning there are no cycles. Okay. Had there been cycle like this. So there are no cycles. If there was cycle in this graph, then execution would not be possible because it'll become circular. And it's like going in cycles to get something done, and it'll never finish. Okay, so good. All right. Yeah, this is the one that shows the concatenate. All right. Now we are talking about collect. Never try collect because it's opposite of parallelize, and it will bring data back to your local memory. This variable, when we execute action such as collect, it brings the entire data to this local variable. Okay, local Scala variable. Okay, and therefore this will be in the memory. So beware of the collect. Collect basically brings all the records to the driver. Take we have already covered. Count we have already talked about. So if there are these many partitions, let's say there are 3 records in one partition. Here, this boundary represents partitions. Okay. Here, while parallelizing, we have explicitly said that we are going to have 3 partitions. I forgot to mention this, that you can explicitly tell Spark to have that many partitions. Okay, even while loading data from HDFS, loading data from in-memory, you could tell how many partitions do you want. Here we are saying 3 partition 1, 2, and 3. This partition contains 3 records, this one 2 records, and this one 2 records. So when we execute something like count, it asks each node that give me the count. Okay, and then it sums it up. It sums it up. Okay, that's how it computes the count. All right. Now, very interesting phenomena called reduce. Reduce basically executes your function again and again until it gets a single value. Okay, it's like applying same hammer again and again or many things such that the output is folded into a single value. Okay? Or you can say that a function is parallelly applied on two values at a time on all the machines and then recursively until we get a single value. Okay? Basically divide and conquer. All right? Make sense to you? No? So there are two variables we are defining here, two arguments. Okay? We're defining two arguments here. Okay? It takes two values, x and y, these are the values, and then it returns x plus y. Okay? And it basically sums up values till it gets 1. So even though sum takes only two arguments, but sum can sum up all the values. Okay? So it's like knowing the addition and applying that addition on hundreds of values. Okay? So here, let's say there are 4 values and we have said reduce, and we want to sum it up. So first 2 values will be applied, then more 2 and so on. So reduce is basically, it aggregates elements of a data set using a function that takes 2 arguments and returns only 1 value. It should be commutative and associative. What does it mean? It means if you apply the same function again and again on the results, the answer should be same. Return type of the function has to be same as the argument. Okay, whatever type you have as the argument should be the same value. Why? Because the output of one execution becomes the input of another, right? Output of one execution becomes the input of another. Okay, is it clear? Okay, good point, Ravi. So we don't have any loop control here. Reduce is doing the looping for us. Yes. Okay, so here we are saying that this is our record. I think the Spark slide is missing for some reason here. Okay, let me just try to create it for you. Okay, we are saying var add, right? And then we're defining a function, defining, let's say sm, which takes x as int, okay, which takes x as int and y also as int and returns an integer, and all it does is it returns, or it returns x plus y. Sounds good to you? Is this function clear to you? Okay, so Spark shell. Okay, so here we go. We're creating an RDD, and then we are defining a function. Okay, let's just check if this function is working well. Okay, let's say we have to sum up 3 values, 1, 4, and 5. So what will you do? First, you will apply sum on first two values, right? And then whatever is the result, we'll apply sum on those. Good? Make sense to you? Now, what if we applied sum in a different fashion? We said sum and then first add 4 and 5, 4 and 5. Will the result be same? Correct. So such functions like sum, where the ordering in which the execution was done does not matter. Such functions are commutative and associative. These are mathematical functions in which commutative means, okay, commutative means that it can be applied on the same value again. And associative means that the ordering doesn't matter. Yes? Now, question to you is average commutative and associative? Can average be done recursively? Okay, let's just check. Let's just define our average function. Okay, let's just define our average function. Let's say we have double value here. Okay, so this is our average. We'll call it AV to avoid the conflict between. Okay, so if we say AV 3 comma 4, what do we get? Ouch, we forgot to divide by 2. Okay, so this is our average function. Good. We are saying AV 3 comma 4, right? Now let's go back to our this example. So we have these three values, 1, 4, and 5. What is the average of 1, 4, and 5? Quickly. Correct. But here it is giving us 2.75. Also, if we change the execution order, we will get the different results. So we defined our function called AV, and we are computing the average of three values, 1, 4, and 5. Okay. This time is 3.75. Earlier it was 2.75. Just the ordering changed. Just the ordering changed. And here the actual value is 3.3 point. So 1.0 plus 2 plus 4 plus 5, right? Divided by 3, right? Sorry. So you can see that the actual answer is this, while once we executed, first computed the average of 1 and 4, and then the sum it up and then compute the average of that is 3.75. Okay. And when we did this way, first computed 4 and 5, and then the result with 1, then we got 2.75. So average is not a valid commutative and associative function. Therefore, you cannot compute average by using reduce. If you have got a humongous list of numbers, you cannot compute average using reduce method. You will have to break down your problem into counting counts as well as computing total. Okay, and in the end, when you get total as well as you get the counts, you can divide the value. Make sense? All right, so that's about reduce. You can see here, the average of 1 and 2 is 1.5, 1.5 and 3 is 2.25, and 2.25 and 4 is 3.15, while the average of 1, 2, 3, 4 should be 2.5, correct? 4 plus 1 is 5, 5 plus 5 is uh, 2 plus 3 is 5, so total is 10. 10 divided by 4 is 2.5. It should be here in the middle of it. While here, when we did this way, the reduce way, its answer is wrong. Therefore, we cannot apply reduce function. We cannot use anything as a reduce function. Okay. Now, question to you is max a valid? Is max a valid reduce function? Anybody? Is max a valid reduce function? If we compute max of 1 and 2 first, and then 3 and 4 and 5 and 6, will it be the same? No matter in what order do we apply? Yes, it will be same. Therefore, reduce is a max is a valid reduce function. So you can see that here the answer is 7. Answer is 7. All right. Is can min be used as valid reduce function? Can min be used as a valid reduce function? Why not? Vikas in charge. Let's say these are the values, okay? And we have, let's say, these values here. How do I quickly? I'll just take example of say 1, 3, 1, 1, 4, and 5. Okay. What's the minimum value of these two? 1, right? What is the minimum value of these two? It is 1, right? Now, if the same thing was done in the another fashion, let's say we first compute the minimum of 4 and 5. What is the minimum of 4 and 5? 4, right? And the minimum of 1 and 4? Sorry, minimum of, this is crazy. Okay, so minimum of 4 and 5 is something, and then whatever is the result, if we apply this same min function again, what is the result here? 4 and 1. So no matter in what order we execute min, max, or sum, the result was correct. A question from Kar: any function that returns single value can be used as reduce function, but it may not always give you the correct result. Average function was returning a single value. We used single value there, but it would give us wrong results because average of two values is not equal to the average of overall records is not equal to the average of averages, right? Therefore average is not a valid reduce function. Do I make sense, Kar? This is a very important concept, and this is something that needs to be understood. Okay, So most of the work, if it is associative, and if a function, if a work can be distributed, can be divided recursively like a reduce function, it is easier to compute those. Okay, so the entire idea about associative and commutative is that associative and commutative functions are distributable. Dividing and conquering is possible in those cases. All right, so we have talked about lazy execution already. So here we talk about the same thing, and here we are trying to think of RDD. Okay, every time we call an action, entire RDD must be computed from scratch. Every time D gets executed, in this D gets executed, A, B, and C would run. When we call a transformation, it is not evaluated immediately. It helps Spark optimize the performance. It is very similar. It is very similar to Pig, Link, and TensorFlow. Instead of thinking RDD as data set, think of it as the instruction on how to compute data. Okay. For example, the optimization. So here we have two functions, map1 and map2. Okay, and we are executing map1 and map2. Internally, it would be combining these two, map1 and map2, into some third function, right? Because both will be executed on the same data, near the same data, and so on. Therefore, this could be optimized. So these kind of operations get combined together and the output goes there. Okay, so that's the idea about transformation and actions. Okay, so a question from RS. So we can only reduce the function which can formulate in recursive equation. Yes, if the order doesn't matter, and in the way it's basically the only way to define it with those mathematical functions called commutative and associative. Okay, in associative the order does not matter, and in commutative where you put the brackets does not matter. All right, so let's take a break. I think we are running late for the break. Okay, All right, so are you able to hear me clearly? Should we start now? Is everyone back? Should we start now? Alvin, April, George, Jiankun, Kar, Krishna, Manu, Mohit, Mohsin, Nani, Narendra, Nitesh, Ravi, Roger, Sudhakar, Sahida, Shamit, Hang, Mahmood, Pradeep, Sunesh, RS, Tamika, Srini, Sunny, Vikas. Good, good. So everyone is back. All right, all right. So we learned a couple of things today. We learned about all about RDD so far. Now, there are a few, caveats to normal working. So when we pass a function, what does it mean? So function passing is something which we have never learned in our normal coding routines. We learned about looping, we learned about calling function and passing the arguments to it, receiving the results and so on. But handing over the piece of code is a difficult concept in the beginning. Okay, so when we pass the function, we could, in case of Scala, we could do it in these three kind of ways. First one is the easiest one, but it's also fairly tricky. Every record is marked by underscore. Okay, you could say underscore dot length less than 10. So this is a very simple way of creating a function which returns true if individual line is having less than less than 10 characters. Okay, if you just want to gather only this one. So this one is the most simplistic way of calling a function. Second way is by using this kind of arrow. We say that our function that we are passing takes one argument called x and then does this. It returns this value. What does it say? Less than 10 and greater than 1. So it returns lines whose length is greater than 1 but less than 10 characters. The third one is where we define the function explicitly and then we pass that function. This is the easiest way to understand, and this is quickest way to get something done. Okay, because the more number of lines a programmer or a coder needs to type, the bad experience, the developer would try to avoid that kind of language. Okay, therefore this would be the easiest thing that you would like to do quickly, and this one is a little more readable. Okay, so in Python also we have similar things. All right, now sometimes you are handing over a function or a variable which is part of some other class. Okay, in Scala also you could define a class and define the argument, you remember, and then inside one of their functions, if you're calling map method or something, it's going to be troublesome. I'll show you how. Let us say this is a normal function is match. Whatever query you're passing, it's just comparing that with the constructor argument. The second function is basically applying ismatch this function on past RDD. Okay, why is this a problem? So when we are handing over this piece of code called ismatch to Spark, it's also going to take with it this variable called query, and this query is part of this whole class, and therefore the entire object will go with it. Okay, it's basically handing over the entire big object. All right. Similarly here we are again referring to query, which is a member variable, and hence it's going to take the entire object. But if you dereference this variable to a local variable here and then pass this variable here, then this is okay because this is a local variable. And this local variable is not referring to any class or object. It is just local variable within the curly brackets. Okay? Therefore, whenever you are trying to pass values, try to drill down to local small variables and then hand over those variables to your functions that is being handed over to Spark. Okay, so keep this in mind. So this is how you can pass the functions in Java. In case you're interested, this slide will be available to you. And there is another transformation called sample. Sample can give you a fraction of the total records, and with or without replacement. Okay, if you say give me sample of this false and then give a fraction, meaning you cannot put it back, which means these records will not have duplicate entries. Okay, while if you say true, which means whatever we took earlier, put it back and then give me zero point 0.1. Okay, so sample is like a filter, right, in which the filter is having a random coin toss. Okay, filter is having a random coin toss, and that's how it is. Okay, keep in mind that number of records will not be exactly 10. If you say 0.1, it's not guaranteed that it'll be exactly 10. All it will do is it will do a coin toss and will check if it is if it is a head or something. So based on the probability, it will compute that to keep a entry or leave it. So that's the way it is. Okay. Yes, zero point 0.1 implies 10%. And it's not strictly 10%. The way it is designed is, imagine that you have to pick 50% of the records, right? If you have to pick 50% of the record, what would you do? You will go to each record and throw a coin. If it's head, you pick it. If it's tail, don't pick it. So chances of 50% record is, that's how you pick it in a distributed way. Okay, in a distributed way, this is how it's done. You kind of throw a dice on every record and then pick something in accordance with the number. 0.5 implies 50%. So George, it's not 5, it's 0.5 for 50%. 0.1 is for 10%. A question from Mohit. Local variable to have the same size and structure as the local object. How? Not really. The overall object here, when we talk about this, overall object could be having hundreds of variables. This class could be having hundreds of variables. So this query will bring the entire object with it. And that's why it'll be huge. And it's going to be further a problem because this function is going to carry this data across the network to many nodes. Therefore, it's going to become a big burden. Did it make sense to you? Imagine that it was having 15 more variables, this class. So we referred query, but query is a member of this particular class, and therefore the entire class is taken with it. Right? A question from Mahmood. Since we are passing Java, does it mean we have to use Java 8? Not really. I'll explain to you. So in Java 8, one lambda expression was created, but ability to hand over the functions was there always. Earlier, we used to do it by defining interfaces and so on. So, so that interface way of handing over the code was there since Java 4, Java 3, I think from the beginning itself. Okay, because you remember in the JWT, I forgot the name, that is Swing and all those libraries. When you generally hand over your function to the framework saying, when this button get clicked, please execute this function. In those cases also, we hand over our functions to the framework, or we hook our function to the events. Okay, so we used to hand over this. All right, so yes, very good question. All right, I hope it makes sense to you. Now, okay, so is it clear why sample will not give you exactly same number of records? Yes. Okay, so if you have to take 50% of record, the easiest way to do is, let's say there are 50 jailers, sorry, 50 prisoners, sorry, there are 100 prisoners and you have to pick up 50 people, right? So what you'll do is you will send many jailers and give them a coin and tell them, if it's a head, then pick the jailer, pick the prisoner, otherwise drop him. Okay, so all the jailers can work in parallel instead of you alone maintaining a list of people and going one by one and then trying to do some random things. Okay, there could have been other approaches whereby we make a list of like 100 people and then randomize the list and pick first 50. Okay, so that's also the case. All right, good. Okay, so here we go. Sometimes we may want to execute, we may need to execute our function against the entire partition instead of entire record. Let's say you want to execute your function for the entire partition. In that case, you could do map partition. You could hand over map partition. In that case, your function would get an iterator as the argument instead of individual value. Iterator is kind of cursor or a list, okay, on which you can iterate. A very important concept, you can order the data explicitly. Unlike MapReduce framework, you did not have a function to order the data. Here, you can order the data at your will. For example, here we are saying that order by this function. And what does this function do? Based on each record, it returns a criteria on which to order the RDD. Here we are saying that return X, which is the tuple, and dot underscore one, meaning return the key. If we say dot underscore two, that means we are saying we want to order by the value. Okay, so this is the way. So we basically give out the key on which we want to sort the data, and our records will be sorted accordingly. Okay, here, because it's a string, when we are putting single quotes, it's a string. Therefore, in this string, one character has got lesser ASCII value than A. And therefore, this data is ordered like this. Otherwise, In the second case, when we are ordering it like this, or based on second value, it get ordered this way. You see that? Okay. So this is how the sorting works. Now, there are some very interesting pseudo set transformations. They are basically libraries, functions built on top of the same MapReduce filter provided earlier. And, and they give you a great amount of parallelism. So these set operations provide you very wonderful things. Imagine, so it basically is not really a set operation. Why? Because in case of a set operation, it should enforce that individual value is unique. There should not be any duplicates, but here it is okay for it to have duplicates. Okay, so it provides you functions like distinct, union, intersection, and subtract. So you can do a lot of magic with the set operations. Okay, do things like find out the students who love geometry as well as trigonometry and so on. So those kind of complex operations you can do. Okay, with this. So distinct gives the set property to your RDD. It's expensive because most of these operations require shuffling. So there are some transformations that might require shuffling. What does it mean by shuffling? Meaning moving data between partitions. So when we say sort by here, sort by moves data from partitions. Okay, the data moves from partitions. And therefore, there will be a data transport involved in sorting. This phase is called shuffling phase while a DAG is executed. When we say XYZ dot action, there are many phases. One phase is where we are doing the translation of data. Then there is a shuffling phase, and then again translation of data, and then shuffling phase, and so on. Okay, so sort by causes the shuffling phase. Okay, sort by causes shuffling phase. It's similar to sorting in the MapReduce framework. Of course, it's not the same as MapReduce framework, but it is similar to MapReduce framework. Okay. All right. So we have a very interesting set operation called Cartesian. Okay. What does Cartesian do? Cartesian basically prepares all combinations. Okay. And it's a very common need at a lot of time. Let us say, I'll give you a very good example. Let's say you want to launch your ad campaigns. You want to launch your ad campaigns and you want to bid on all kinds of keywords. Okay, all kinds of keywords. Let's say thrilling big data course. That's a keyword you want to bid on Google, or or great big data course, or practical big data course, or mm, nice big data course. So you want to multiply nice and on the other hand you could have many other courses to sell, so you could create a permutation of both the things. Okay, great big data course, great Scala course, great Spark course, great this, great that. So you want to multiply adjectives with the nouns. In those cases, you could use Cartesian product. Okay, in a classic database joins, when we join two tables, table A and table B, without a where clause, we get a Cartesian product between the records. If table A has 10 records and table B has 15 records, the result of joining table A and table B without a where clause would give us the total number of record as multiplier of first set of record and second set of record. So 10 records into 15 records is 150 records will be the output. Same is here. We have RDD1 having 3 records, RDD2 having 3 records. The output is 9 records. User 1, venue 1, user 2, venue 2, user 3, and venue 3. All the permutations are created. Okay, is the quotation clear to all? All right. So here are a few of the questions. All right. Yes. Okay, who will give me the answer for this question? So we have one RDD called noun and second RDD called adjective. And we are saying Cartesian on both of those. What will be the result? We are saying adjective dot Cartesian noun. So adjective will come first and then the noun. That's right. That's right. Yes. Thank you, Krishna. So this is how it would come. Okay, good boy, good girl, bad boy, bad girl. So that's how it will come. Okay, so it basically multiplied the list of nouns against list of adjectives. All right. Now let's move on to, so there is very interesting function called fold. Okay, it aggregates the element of each partition and the results of all the partitions using a given function and a neutral zero value. Okay, so yeah, so it's very similar to reduce function, just that the initial value, the zero value, you can provide. Okay, you can provide the zero value. This is very great for the cases where both of your arguments, basically your output argument is not same as the input. Okay, so fold is great, and so it always goes like this, and I'll try to explain to you. So fold also does the like reduce. All right, let's imagine that these are your values. Okay, and the output is, let's say, some other data type, not same data type as your, this is your RDD. So you define a initial value. That's the value you are passing in the fold argument. Okay, you pass a initial value and then you join these two. Okay, and it should give us a round object, and then both of these will be combined, and again, okay, and then it'll look like this. Okay, so makes sense to you? All right. Okay, so imagine that what you want to do is you want to convert these values like 1, 2, and 3 into comma separated values. Okay, So what will you do is you will define your initial value as empty, and then you will let them concatenate. So here it'll look like empty comma 1, then after this empty comma 2, and empty comma 1 comma 2 comma 3. So basically you could define an initial value and then a function to combine initial value and this value and get the results. Okay, this is great for the cases where your output is not same as input. All right, but a more flexible function is aggregate. This is a very important function. So we faced a problem with the reduce function, and the problem with reduce function was the output data type of a reduce function should be same as both arguments, and both the arguments should also have the same data types. So return value and both arguments of reduce function should be exactly same data type. And that's not a great idea. That's not a great thing, because that restricts us from many things. And that's where a function, very generic function called aggregate was created. A very generic function aggregate was created. So aggregate takes three things: initial value, sequence operation, and combination operation. Just a second, let me, yeah. Okay. All right. So first, all the values of all the partitions are merged to a single value, initial value, using sequence operations. Okay. And then this combine operation is called. Okay. And then this combine operation combines the two values from both the partitions. And then, and then, and then the result is given as the output. All right. So in these cases, basically, this is kind of more flexible form of reduce function. All right. So this diagram would make it more clear to you. All right. So here we are trying to compute the sums, counts and sum, both of the things. So this will basically compute first the sequence operation. Initial value is 0, 0. As I was telling you earlier, that how would you compute the average of the total, right? You will both compute sum and the count, right? You will compute both sum and the count. So you define a function. You define a function which basically does the counts elements and as well as sums up the things. So you define a value, initial value, 0, 0. This is the sum, this is the count. Okay. And then we define a function called sequence function, which takes two arguments. Okay, which takes two arguments. One is a tuple, other is an integer. Okay, so this tuple is the initial value, and this is the individual value. So this tuple, so this is the initial value, right? This is the initial value. To the initial value, we add the value, the sum, and the count, which is second argument, this one, gets incremented by 1. Okay, so okay, let me take a step back again. So what is it that we are trying to compute? What is it that we are trying to compute? We are trying to compute the average, right? How would you compute average? By first computing sum and then computing the count. This could have been easier. This could have been far more easier if we basically first computed count and then computed total. But they could have been two separate shuffling efforts, not shuffling efforts, two separate chain of processing, and it could have been far more time consuming. So why not do counting as well as summing up together? Okay, why not do counting, uh, why not do counting and summing up together? All right, so let me take a quick example. I think this will make more sense. This will make more sense. Okay, so here let's say 1, let's say 4, and say 12. All right, good. An initial value, so this is the number that we're going to keep in mind. Oh, okay, and we're going to say this is the initial value. Okay, what should be our initial value whenever we are doing count here? Quickly, we are going to say initial value is 0, 0. So the first number, first of this one represents the sum, and second one represents count. Okay, when this and this value is combined, so what will we do? What will be the value of this? What will be the value of this? Quickly, 1, 1. Perfect. And what will the value here? Who can help me? 2, not 2. The first one is sum and second one is count. It'll be 5, 2. Correct? Again, the second element will be added. So now it will be 17, 3. Now remember that same thing would be happening on other partition. There could be uh, another partition somewhere. Okay, there could be another partition somewhere here, and from there, after all of such similar computation, there could be similar computation going on there, and there could be let's say the value that has come on the other partition is let's say after all of these computations, let's say we came up with 34, 6. Okay, now these two needs to be combined together, right? These two needs to be combined together. So the argument for this function is different. Here, this function is taking two arguments. One is of tuple type, other is of tuple type. While this function that was converting these two, one was tuple and second was a number, right? Therefore, there has to be two functions. So we say, so there will be two arguments. First one is a tuple, second one is a tuple, and we sum up these two values. So it'll be 51, and then 3 plus 6 is 9. Okay, and this way you can get, now we can, in the last, once everything is done on the local machine, we are writing a separate instruction to divide 51 by 9, which is 17 by 3, and which is whatever. Okay, do I make sense to you? So we need two kinds of functions. We need two kind of functions. One is this, okay, one is this kind of function, okay, and other is this kind of function. All right, did I? Correct. A question from RS is, but we can get the count of length of an array. Why should we even use the count? Okay, very good question. Anybody has an answer for this? Okay, I'll explain to you. Let's say my data is equal to source data dot filter. Okay, and and after filtering, we are saying, you know, clean records is my filtering criteria. Then after filtering, we are saying map as in um, translate to or parse to numbers, right? Now, question is, we do not know how many records will be there in my data. Length or count. Length is computed by count. Count is going to make a call to both of these functions. Okay, whether count or sum, both are going to make the call to this. Okay, so if we say my data dot count, right? If we say my data dot count, it's going to compute source data, then apply the filter on this, then apply this map function on this, and then do the count on all the partition and bring it back, right? And similarly, if we say my data dot reduce and we are passing the sum function here, right? So sum again will go to, will do this computation again, right? We'll do this computation again and bring you the records, right? So your average function might look like this. Your average function might look like this. It's pretty easy in our world. So you can see my data dot reduce divided by my data dot count. But the problem is both of these functions are making duplicate calls to these. Do it make sense, RS? This one will start computing my data entirely. And similarly, once that computation has resulted in a local variable, then the second computation will start. And this will also result in a local variable. Yes? Although some of you might argue that we could use cache, right? We could use cache. And caching basically brings, cache does this computation once, but it consumes memory. Okay, so to avoid this dual scan, we are trying to do it in a single shot. Okay, do the computation of count as well as sum in a single shot. Do I make sense to you? No? All right. So that's how we got the sum as this, count as this. We can divide it later now. And why did we need aggregate function for this kind of work? Because reduce function cannot achieve this. Reduce function cannot have separate combination between two partition and separate sequential operation on each partition. All right, you remember this diagram? Here, the behavior on each partition is different from behavior of across the partition. Each partition will compute their tuple by counting and summing up, while across the partitions, finally, this one is happening on the driver. It's taking value from all the partition and then combining those partitions together by summing up their sums and counting the count, summing up the counts as well as summing up the sums. Okay. So this is the heart of distributed computing and parallel computing. And most of the mathematics that you see, machine learning library this, machine learning library that, on Spark, they're basically implementing similar functions using Spark core. Okay, like matrix multiplication, like various kinds of mathematical models. They're actually breaking it down into mapper reducer, mapping, reducing, flat map, filter, and count, and so on. And basically, using these kind of techniques, they're breaking down the logic into distributable and then getting it done and calling it their machine learning library. All right, it's hard, but it's very important to understand the basic construct. All right. Sometimes you just want to generate summary. Word count actually can be done easily by using count by value. Okay. Count by value. Count by value basically gives the entire result in the memory instead of giving it in the disk. Therefore, count by value is not a great idea. Okay. Count by value is it'll give the frequency of each element. Okay. We can get the top n elements. Okay. And yeah, it basically sorts the values and gives you the highest 10 records. Okay. And sometimes you may want to specify your function on the basis of which you want to you want to define the criteria. For example, here we are saying that give me the reverse ordering on this. So you can take order the data by your choice here, and then retrieve the results. Okay. So that's how you can achieve the top n numbers. Okay. And okay, sometimes you would like to apply a function to all elements of an RDD, this RDD. It's not a great idea. It's not a great idea, but it is there. It's a sequential function. All right. So now persistence, but every RDDs are lazily evaluated, and RDDs and all of its dependencies are recomputed when you call an action. We may wish to use the same RDD multiple times to avoid recomputation. We can persist the RDD. Okay, to avoid recomputation, we can persist the RDD. Remember, there's just one example, the one which we said. This is where the persistence comes into play. We could cache the value of this one on every node parallelly and then use that. Okay, so that when we call reduce and count, it would not really recompute my data. It won't really recompute my data because my data is cached, but reduce function will be called on the entire data. All right. Okay. Now, very important part. We have already covered it. A question there was earlier that what happens in case something fails? Since at every point, Spark knows how it computed an RDD, how it computed what is the graph. Since Spark knows that, therefore, that particular partition was easy to bounce. Similarly, when we do the persistence, same applies to persistence. Persistence means we are caching the value. We are not going to recompute the value on an action. Instead, we are going to use the previous value. Okay? If a node that has data persisted on it fails, Spark will recompute the lost partitions of the data in the same way it does when we call an action. Entire thing will be recomputed. We can also say that while caching, we could say that replicate it, meaning copy this cache on other machines, on more than one machine, so that the recomputation would not happen on failures. Okay? Recomputation would not happen on failures and the overall process will become faster. Here's an example of caching. Okay? So we basically say dot cache and it does the caching. All right? There are three kinds of caching. Memory only, not three kinds, there are quite a few. I'll explain just now. So a cache can be kept in the memory or the disk or both. Okay. And similarly, we can save cache in as a serialized Java object. Okay. and you know it's easier to serialize using the Java objects. Okay, there are other modes of serialization as well. Then we can also say that use memory and disk serialization. With serialization, we could also say that the while caching, how many numbers of copies do you want? Okay, so we have 4 arguments: whether you want keep in memory, whether you want to keep in disk, whether you want to keep it serialized, or whether how many number of copies do you want. And there is one more experimental. All right, so the easier way in Scala is, you in your code you first import the storage. Okay, and then you define this object. First one means use disk, second one means use memory, this one means of the heap. Here we are saying don't use of the heap. And then third one means whether serialized or not. And fourth one is how many copies of cache do you want? Okay. This, once you create this object, then while persisting, you could pass this object in the argument. Okay. This way, it will save this RDD so that it does not really recompute it on the next call. All right. And now keep in mind that this is only true. This is only true for during the process. This variable would not exist after the process has finished. Okay, between 2 actions, this will not be available. Not between 2 actions, it will be between the 2 sessions. Okay, be between the 2 sessions. All right, the way our console is open, so that's one session. Okay, so that was caching and our basic understanding of Spark. All right, a quick overview of key value pairs in Spark. So there are key value pair RDDs. They're nothing but okay, the special operations are available on key value pair RDDs. Okay, if you try to call the key value pair kind of operations on non-key value, it'll give an error. Okay, say for example, we have input data. This input data means it's a list of key and value. Each record is made up of 2 elements. So how many records are there quickly in input data? Yes, I think everybody has gone to sleep. Okay, all right. So some are awake. So how many records are there in this input data? Correct, it's 4. And each input record is of which data type? What is this data type? Tuple, correct. It's a tuple of integers. Good, good. So this list is made up of tuples. Tuple is like couples, like X and Y. And then um, there we basically are saying parallelize it, meaning convert it into RDD with 2 partitions. Okay, if we say 3 partitions, there'll be 1, 2, and 3, and there will be one partition containing 2 tuples. But we cannot have more than 4 partitions for it, right? Record is non-breakable. Okay, a partition would minimum contain 0 record, okay, or 1 record. Partition could be empty sometimes, okay, but you can always coalesce them and then remove the missing parts. All right, there are functions to do that. Now we can reduce by key like this. See, a tuple will come as an argument and then we can sum it up. Okay, so what is happening here when we say reduce by key? This data is going to be ordered by the key. Okay, this data is going to be ordered by the key and grouped by the key. So 1 2 1 3 and 1 6 will get grouped together. So our function will be called twice. This function will be called twice. Once 1 comma sum of 2 comma 3 comma 4. Okay, and 2 comma 3 comma 4, right? Not 4, 6, sorry, 6, right? And then it'll be 2 comma sum of 4, right? Now remember that when we say sum of more than 3 values, it's going to break it down. First it'll sum up these two and then sum up this, correct? So it'll be 2 plus 3, 5 plus 6 is 11, right? This is what it is going to be. And this one, there's no need of any operations. Is it clear to everyone? So again, the function that you're passing here, this function is going to be called on every value for each key, right? To aggregate it. So it has to be again commutative and associative. You remember word count? In word count, we use this function, reduce by key. Okay? So first we converted our words into pairs, right? Into tuples. And then on the tuples, we called reduce by key. All right? Okay. So we can actually use flat map, or any other function to convert things into key value pair. Okay, sometimes you want to just get the keys. There's a function, there's a attribute called keys. It gives you the list of only the keys. Similarly, there is something called values, which will only give the values. And that's basically an RDD. You might have to collect it again. And sometimes you just want to run a function as a map on each value. Say, for example, you just want to increase the value by 1. So you can do that by doing the map values. Similarly, flat map values, then reduce by key, which we have already gone through. Okay, reduce by key. And this is how it will look like. So if we are saying map values, this is getting converted. So panda is getting converted like this. So we are saying 0, 1, 3, 1, and so on. And then reduce by keys, basically bringing all the values of panda together. Okay. So this is what we were doing earlier while we talked about word count. So we converted into tuple and then ran this operation. All right. So we have already done this part. Okay. Sometimes we may not want to group the data. We may not want to aggregate the data. We just want to group the data by key. So in that case, you can simply group the data and iterate over the values by collecting it and printing it. Okay. All right. Now, remember aggregate function? Sometime there is a further more granular function called combine by key. Okay, combine by key is again a very powerful function. Okay, so you define 3 functions: combiner, create combiner, merge value, merge combiner, and so on. Okay, and so basically, let's say these are the 3 values in your partition, RDD partition. This is blue box. We want to convert it into what color is that? Yes. What color is that? Yellow box, right? right? So let's say these are the records we want to combine together to get the yellow box. Okay. Now, as we talked earlier, reduce function can only give blue box from a blue box. That too, both boxes need to be blue. So we might need to define two kinds of functions. One that translates one blue into green, right? Then second function that combines a green or yellow, I don't know what color is this. I'm a colorblind person. So yellow, so first function is converting blue into yellow, and then second function is combining a yellow and a blue to give something, and third function is combining two yellows to give yellow. See, there are three different kind of functions because of the data types. Therefore, it's very important to understand that these kind of things are possible when you face these kind of circumstances where there's a data type issue or there are different operation you want to do while combining different kind of values. Then you may want to use either aggregate or combine by key. Okay, aggregate or combine by key. All right. So there are quite a few transformations on key value pair similar to normal RDD. You have sort by key and you have subtract by key, the set operation. And the most important part is join. Join basically joins two records. You see, if X is having A1, B4, these are two records. Imagine that there is a table having two columns. First one is string, second one is a number, and two records A1, B4. Similarly, Y is another table A2 and A3. So first value is a key, second is a value. Therefore, when we join X and Y, it will be joined based on the key. So it will result in A1, 2 and A1, 3. Sorry, it will be B1, 4, 3. Okay, it will be B. Here it will be B and 4, 3. Okay, let's just take a look if it's working fine. Okay, so that's X and we defined Y. You can see, sorry, right. So we are joining based on A, so it'll be A1, 2 and A1, 3. Yes, this is correct. Yes, I was wrong. So basically we are joining it. Joining means take a value from one side, take another key from another side, and then try to find out the same one. Therefore it'll be A1, 1, 2, A1, 2, 1, 3. Okay, B will be dropped because there's no corresponding thing on the other side. Joining is pick up key from both the side, try to find the similar key on the other side. Yes? Yes, thank you, Sudhakar, and thank you, Hang. Right. That's right. Thank you. All right. Now, similar to SQL, it also has left outer join. Okay, left outer means for everything in left there has to be everything from the left goes into output, even if there is no corresponding key on the right hand side. Even if there is no corresponding key on the right hand side, all of the keys from the left hand side go into the output. That's left outer join. If it's found, then it's great on the right hand side. If it's not found on the right hand side, put none there. For example, here You have X, which has A and B, right? We have Y, which is A and 2. When we say X left outer join Y, which means A is found, correct? A is found, but B is not found. Therefore, for A, both values from both sides, 1 and 2 is combined, while value of B is not found on the right hand side. Therefore, it's combined with none. All right. So that's how it works. Yes, quickly. What will be the yes? Question from Sudhakar is what is sum? Sum means an array of values. Okay. Sum is a parent class of an array in Scala. Okay. What will be the result of outer join here? Left outer join quickly. So our answer will be 1 Sandeep and Ryan, correct? And 2 Shravani, none. Is it clear why? Because left outer means take everything from the left in the output. From the right, if it's something is found, keep it, otherwise put none. Okay, none is equivalent of null or empty from other corresponding values. Okay, in SQL you have null. Okay, so there is something called co-group. Co-group is basically for each key in the cell for the other, return the resulting containing the tuple with the list of value. Co-group means joining and grouping. Joining and grouping from both the sides. Okay, that's what is co-group. All right. Okay, so it also, like Microsoft Excel, it also has a lookup function, and you can look up by key in case of an RDD. Okay, it would require a shuffling on the data side. All right. So if you have already a sorted uh, RDD, it will make a note of that part and will operate really fast. Okay. So a quick project to all of you. In this data, find top 10 IP addresses. Okay. In HDFS, this folder contains certain files. Find the top 10 IP addresses of the users who are trying to access this website. Okay. So here is one solution which I have provided. You can try by yourself. Okay. All right. So that's pretty much for today. Tomorrow we are going to discuss streaming and some more operations in Spark core. Okay. And we will also talk about stream processing. And I would require around 3 to 4 more hours during the week. Okay. That's an overflow. Okay. So I'll need 3 to 4 more hours during the week so that I can cover Spark SQL, MLlib one example, and GraphX one example. Okay. So I would love to have 3 to 4 more hours, maybe over 2 classes, 2 hours each. Okay. 2 classes, 2 hours each. Okay. During the week. So tomorrow we will talk about some more operations on core, understand a little bit more advanced, and then we go into the stream processing with Spark. All right, we will be using Kafka as well as the IP addresses. Yes, everything will be recorded. Thank you, Elvin. Okay. So same start time during weekday also works for others if we have similar time during the week. Okay, for Vikas it's hard. Oh wow. Okay, okay. I understand totally that it's not a right thing, and yeah, IST for me I can manage any timing because this is my first priority. Okay, okay. Let's think about the possibilities, and tomorrow if we can reach to a conclusive time, it'll be great. All right. Okay, we can have this discussion over the email. Okay, I'll start the thread and then we can have. Okay, because I love to close this tomorrow, and yeah. Okay, I'll drop you an email, all of you, so you give a convenient timing, and that'll be good. All right, and then we can have quick discussion tomorrow. All right, I look forward to see you all tomorrow, and we will have further more interesting things tomorrow. Okay, tomorrow we are going to try more and more hands-on with specifically with the stream processing. You can't really learn anything without trying it out. So one example at least we'll do it together. Okay. All right. Thank you very much. And I look forward to see you tomorrow. Bye-bye. Have a great